Welcome to Let's Get to the Marks. This one's on calorimetry and bond enthalpies. So let's go 5 or 5.1. A student is provided with 0.03 mole of a sample of an alcohol. The student decides to identify the alcohol using an experiment to determine the enthalpy of combustion. Figure 2 shows the apparatus used. We've got 0.250 kilogram of water. That's the mass. We've got a temperature increase of that water from 18.9 to 17.1. And we're using the specific heat capacity of water, which is 4.18 joules per gram per Kelvin. And we can use this equation, Q equals mc delta T, where the Q is the energy transferred and the delta T is the temperature change. Let's work out the enthalpy of combustion in kilojoules per mole. So we need to do the mass times the specific heat capacity times the temperature increase. Now the mass is in grams, so you need to convert the 0.250 kilograms to grams. So times by 1,000, so you've got 250 times 4.18 times 59.2, and that's going to give you 61,864 joules. That is your energy transfer, but that is in joules. Now you can see our answer is supposed to be in kilojoules per mole. So we need to divide by 1,000, 61,864, and that will give us 61.864 kilojoules of energy was transferred into the water. Now our final answer needs to be in kilojoules per mole, or mole to the -1, which means we've got to divide kilojoules by moles. And we're given the moles this time, 0.03 moles. Sometimes they give you the mass in grams of the fuel and you have to convert that into moles using the MR of the fuel. This time we haven't had that extra step. It's only 3 marks. So you just do the kilojoules divided by the moles and we get 2062. Now, because this is a temperature increase, this means it's exothermic. Energy has been released to the surroundings. So we would have a negative symbol for our enthalpy of combustion. So you'll need to put minus 2062. You can always do the 18.9 minus 78.1 so that the temperature you receive here for M1 is minus 59.2 as the temperature change. But I just like to look at the question and see if it's exothermic. I stick a negative symbol. Okay, let's go into 5.2. Table 2 shows the enthalpies of combustion of some alcohol. So we've got ethanol, propan-1-ol, and butan-1-ol. And we've got the enthalpy of combustion in kilojoule per mole to the -1. Explain how your answer to question 5.1 suggests that the alcohol is butan-1-ol. If you've been unable to obtain an answer for question 5.1, assume the answer is minus 2,120 kilojoule per mole. Okay, we actually got an answer. The correct answer from 5.1 was minus 2,064 kilojoules per mole. And at first glance, you'd look at propan-1-ol and go, if I had to choose which alcohol this is, well, propan-1-ol's result was minus 2021. Surely that's closer, and surely that means that the alcohol that we just burnt is probably propan-1-ol, right? Well, actually, that would be incorrect. And the reason is when you do calorimetry, you will always get an undervaluation. Your answer will be less exothermic than it should be. So although we got minus 2064, it should actually have been a bigger number than minus 2064, like minus 2400 or something like that. Or in this case, butan-1-ol, which is the likely answer, minus 2676. So you're always going to lose some heat to the surroundings through the glass and into the air when you do calorimetry. And also, some of the butan-1-ol may not have undergone complete combustion, and incomplete combustion produces less heat. It's less exothermic. So your answer will always be less exothermic than the real true answer. So if that means that our answer of minus 2064 is less exothermic than the real answer, then it can't be propan-1-ol. Okay? It can't be propan-1-ol because our answer is more exothermic than the true answer for propan-1-ol. How did we gain extra heat when we're losing heat? So that's the reason why the most likely identity of our alcohol is butan-1-ol. And the reason that the answers are not identical is because it looks like we've lost almost 612, something like that, 612 joules, or kilojoules, per mole to the surroundings, or via incomplete combustion. And so that's the answer for 5.2 and explains why we've got an undervaluation or a less exothermic answer, which is what you get with calorimetry. Okay, we're now moving on to 5.3. The equation for the complete combustion of gaseous pentan 1-ol is shown. You have the equation here, written in all its glory, with an enthalpy of minus 3,388 kilojoules per mole, or minus 3,388. We have a table of the bond enthalpies, and it says use the data from table 3 to calculate a value for the mean carbon-carbon bond enthalpy in pentan 1-ol. So you've done these before. You're simply going to work out the total mean bond enthalpy of the reactants minus the total mean bond enthalpy of the products equals the enthalpy change for the reaction. And then you need to solve it to find out what the CC bond is. So I'm drawing out the pentan 1-ol in order to count the number of bonds. So it looks like I've got 4 CC bonds that are unknown. And I have like 11 CH bonds. So I need to do 11 times 412. I need to do 1 times CO and 1 times OH. And then there's 7.5 oxygens. I've also got to do 7.5 times 496. And if you smash that all into the calculator, you're going to get 9075 kilojoules. So on the left-hand side, or the reactant side, we have 9075 kilojoules. Now I need to add up the products, and I've got 5 carbon dioxide. So how many COO bonds are there? They're worth 805 each, you can see in the table. And what have we got here? So 805, I need to times that by 10, so that's going to be 8,050. Why do I need to times by 10? There's 2 C double bondo in the carbon dioxide. You get what I mean? And then the H2O, a water molecule has 2 OH bonds. So as there's 6 water molecules, there's going to be 12 times 463. And if I smash that all together, I'm going to get a total bond enthalpy of 13,606 for the product side. Now, if we do the reactants minus the products, you get the overall energy change, which is minus 3,388, which they've given us. So we now need to just solve this to find the CC bond. So first of all, let's add 13,606 to both sides to get rid of the minus 13,606. And that leaves us with 4cc plus 9075 is equal to 10,218. Now I want to get rid of the 9075 to leave the CC bonds on their own. So I'm going to minus 9075 from each side. And that will get rid of the 9075 on the left. And it's going to reduce my right-hand side as well. So this ends up with the 4 CC bonds equaling 1143. Now I want to find out the value of just one carbon-carbon bond. So I'm going to divide by 4 and I'm going to get 285.8. You can round that to 286, but they'll give you the mark for 285.8 or 285.75, whatever it comes up in your calculator. You'll get the marks for that. And there we go. Lovely jubbly. There's quite a few points here where you could have picked up a mark in the working out. Okay, let's move on. 5.4, this is the final part to the question. The energy stored in this fuel can be compared using energy density values, and they're measured in kilojoule per dm to the minus 3. Okay, so the amount of energy per decimeter. Calculate the energy density of butan 1-ol. So we need to calculate how many kilojoules are in 1 decimeter of butan 1-ol. Well, we know the enthalpy of combustion is minus 2676, and we've been given the mass, the density, which contains the mass 0.810 kilograms in 1 decimeter, and we've been given the MR. And even if you're baffed by this question, the moment you see MR, you should be thinking M mass over MR times moles. Now we know that in 1 decimeter there's 810 grams because we do 0.810 kilograms times 1,000, and we know that we've been given the MR of 74, so I'm just going to do mass over the MR, and that's going to give me the moles. And that means there are 10.95 moles in 1 decimeter. I now need to work out how much energy is stored in 10.95 moles. Well, I've been told the kilojoule per mole is minus 2676. So I just need to times that by 10.95 to find the total amount of energy stored in 10.95 moles, which is the amount of energy in a decimeter. And I'm going to get 29,291. You could write minus 29,291 if you want. Sharing's caring, people. Hit the like, punch the bell, subscribe. Let's get to the marks.
You're still here? It's over.